Oh, right. It's the old faithful that are arriving.
The old faithful.
Well, yes.
The only reason I missed last week was my wife's, well, pregnancy appointment. It's not hardly just my wife's.
Oh, excuses.
Yeah, and priorities and all that.
Yeah.
Well, like I said, if just one person is interested and might benefit, then that's fine by me. It helps me sort my mind through when I'm trying to collect my knowledge of physics as best I can. And at the moment, I'm still reading through Feynman's lectures. I read the book 3 about a month ago, which is QM, Quantum Mechanics, and then I'm just wading through book 1, which is it's quite hard to go through because there's a lot of words, and there's a lot of it that's for me was high school physics, but nevertheless there's a lot of stuff that shows up in there with insight that is just brilliant. I mean, it's just ridiculous how easy physics he makes it seem. I mean, you know.
That's somebody who knows it well.
Hmm?
Anybody who makes it sound easy.
Yeah, that's right. Okay, so why don't I get started? Again, if there's anybody, Tom stumped me on a question just now, so we won't go into that. But if anybody wants to mention anything, please do. Okie dokie. Assuming that everybody's not frantically pressing their microphone button, I'll get going. So now we're down to the point where we're embedding all these atoms and their characteristics into a real plasma. So now begins the actual subject that we're talking about. Again, I want to remind you of some very nice, my favorite one is probably Cooper, the plasma spectroscopy. It's quite a long book, and I think it may be Jinx Cooper. He was at Gilla. I had an office next to him, which was great, and we used to chat about a lot of stuff. I think it might have been related to his thesis that he wrote this, and I believe perhaps he did it at University College London, though I'm not sure. Anyway, that's a place where University College is a place that specialized in spectroscopy, astronomical spectroscopy, and also in the atomic physics and molecular physics. But any of these will shed some interesting light. Plasma spectroscopy by Cooper is the one that's the most elementary physics, from an elementary physics point of view. And so if you wanted to solidify anything, that's a very, very good place to start. As I mentioned, it's complete up to the point where something called dielectronic recombination was included, which is basically a many-body problem. So it's pretty up to date. It's not completely up to date. Obviously, there have been some discoveries, but the essentials of plasma spectroscopy are already there. So let's just remind ourselves of what conditions might look like in certain kinds of plasma. First of all, we have the thermal equilibrium, and from our undergraduate days, we should be able to remember that what this corresponds to is in sort of Boltzmann, Maxwell-Boltzmann kind of argument that if you have a dense enough plasma so that, or bunch of kinetic particles moving around, it doesn't need to be a plasma, it could just be a gas, then providing you have detailed balance between processes. What do I mean by that? So, for instance, a particle hitting another particle, and then that's going on with some probability, then the rate at which that's happening, the probability per second, should be balanced by this reverse process. So for instance, if you have ionization, you'd have one electron going in, knocking 2 electrons off, or knocking 1 electron off, so there'd be 2 electrons going out. And the reverse of that would be 2 electrons coming in and 1 electron coming out. So that would be a balance between a 2-body collision, an electron and an atom, and then causing there to be 3 particles. So you'd have an ion and then 2 electrons. And then in reverse, you'd have 2 electrons coming in and then 1 electron going out. So providing all those kind of processes are in detailed balance, that's the basis on which statistical mechanics and thermodynamics are linked. And so if we go a bit further than that and say, well, we've got 2 kinds of things going on here. We've got particles, if you like. I mean, you know, wave particle it's all part of the same deal on the micro scales. But you've got a pool of photons as well as a pool of particles. The distribution functions of those two things need to be the same in order, or will be the same in order that they satisfy detailed balance. So what this means is that the pool of photons, you can imagine sending a photon in, ionizing an atom, knocking an electron off, and then you can have an electron coming in and in reverse and emitting a photon. So that would be two body processes. Remember, the first one I mentioned involves 3 particles coming in reverse. This one involves just 2. So what we have here is if those are all in detailed balance, if the density is so high and the density of photons is so high and the photons are not escaping from this region, so there's an imbalance in the amount of photons in their distribution function, the distribution functions are going to be thermal ones, and those thermal distribution functions we'll get to shortly. And this kind of thermal equilibrium never really happens unless you contrive it to do so in the laboratory by putting in a black box with, keeping it warm all around and nice and cozy, and putting a tiny little hole in so you can observe the radiation, etc. In the middle of a star, it's approached because you have small photon and particle mean free paths, but there is a net flux, radial flux out from the nuclear generation region. And of course, the nuclear reactions in the middle drive an imbalance, which drives the flux of radiation out. But essentially, if you were to look at the distribution functions right in the middle of the sun, they'd be very, very, very close to a Maxwellian distribution because of this. Then there is, as we go, now we come up further out in an atmosphere of the star, say, and we say, well, we can allow we know that photons can have a very long mean free path. I mean, we can see photons from the other end of the universe, but it's very difficult to measure particles at the other end of the universe. So all astronomy is about, or it was about, just measuring the photon distributions, because we know that those interact, but they don't interact strongly enough with the plasmas that they're trapped where they sit. Otherwise, we wouldn't have astronomy. So the photons can have mean free paths from sort of essentially infinity, go on forever around the universe, down to when there is plasma there, or gas particles that can absorb or scatter these photons. And so the photons can be decoupled from the plasma. So what we have is something called local thermodynamic equilibrium, where the particles are described by Boltzmann distributions, Saha-Boltzmann we'll get to shortly, because of very high particle densities, and the collisions are in detailed balance. So the collisional processes are all balanced, but the photons are not. So if you imagine sitting at the top of the photosphere, you can imagine having a case where all the particles collide so rapidly with each other that they relax to their equilibrium, local equilibrium value, providing the photons don't drain out energy from that parcel of fluid very quickly. And so this is a condition that we call local thermodynamic equilibrium. You can read about this in books by Mihalis, by Chandrasekhar, all the people. And it turns out in the photosphere it can be a very good approximation for things like a source function and an optical depth, which we'll get to later. But what it means is that essentially the particles, for whatever reason, are held in this state, and you can define every single probability of an atom in local thermodynamic equilibrium in terms of 2 quantities: 1, the density of the particles, and 2, the temperature. But the radiation field can depart from a Planckian. And in fact, if you look at the photosphere of the sun and imagine sitting there and looking down underneath you, you see a Planck function of radiation coming from these particles that are underneath you that are gradually escaping. But if you look up, you see space. So there's obviously an imbalance there. So it cannot possibly be in thermal equilibrium, but it may well be in a very good close approximation to local thermodynamic equilibrium. Okay. Now, let's go to the very bottom one first, the coronal equilibrium, or nebula equilibrium, if you like, or in the interstellar medium. The densities in these plasmas, which are often very, very big. We showed the Ring Nebula. That's a big old thing sitting on the sky. early on in these talks, and the densities there might just be 10 to the 4 particles per cubic centimeter, as opposed to 10 to the 19 or whatever it is in our atmosphere. So this is a fantastically good vacuum, but it's big and it's glowing, and so we can see the net effect of this big plasma, lots of electrons inside it, radiating. And under those conditions, and also in the corona, we have such low densities that we must consider only 2-body collisions. Remember, we talked about thermal equilibrium at the beginning there, and if you imagine an electron going in, whacking an ion, and knocking an electron off with 2 electrons going off, the reverse process is proportional to the density of the electrons squared. So if you really drop the density of particles in the plasma very quickly, then those 3-body problems, those 3-body collisions drop out. So this is way out of detailed balance, way out of equilibrium, and instead you have a balance between the most probable things, which turn out to be 2-body collisions. 1 particle in, 1 particle out, that kind of thing. And so this is very, very far from a Saha equilibrium, which requires the 2 bodies in and 1 body out, and vice versa. So what we have here, we have absolutely no detailed balance, but we can have a statistical balance. What that means is simply that while we don't have reversible processes, detailed balance, what we do have is reciprocal processes don't balance out, but you have a balance between the dominant processes, like an excitation of an atom and then radiation out, which is most definitely not an equilibrium situation. But nevertheless, you can say, well, maybe the plasma in the nebula or in the corona is sufficiently steady on some scale that you believe that there's a balance between these processes that are left over, but it's very far from thermal equilibrium. So in a case like the corona, essentially 100% of the electrons photons will escape from that, showing you indeed that this cannot possibly be close to any kind of equilibrium. One should remember that in the corona, you've got radiation again streaming from the surface of the sun, and it's got the spectrum of the sun as we observe it is going to be the spectrum that the corona observes it, because there's almost nothing else left to absorb the photons between us and the corona. So the corona is going to, apart from the effects of the corona itself, is going to see the radiation we see. So you can imagine now having that, and that's an enormous flux of radiation, right? But it's an enormous flux at very particular frequencies, namely in the infrared and in the visible. It drops off like a rock in the UV, with 1 or 2 exceptions where the UV lines are. So what we have is we have that plasma is now irradiated by this relatively low energy radiation going through it. In between the corona and the photosphere, so in between the bottom and the top points here, we've got a condition which is sort of the worst place to be in the sun. And that's where, in terms of this thermodynamics of things going on. So as we imagine crawling out of the photosphere and we're coming out, then you're getting more and more photons leaving into space, because as you go up, the mean free path of photons drops because the density is dropping in the potential well. And then these photons have a longer and longer path length until finally we see them. So this is why it's very hard for us to see the chromosphere unless we focus on, with our eyes, unless we focus on something like H alpha. It's because all that plasma that's in between the photosphere, which has a huge density of 10 to the 17, and the corona, which has a density of around 10 to the 9, 10 to the 8 particles per cubic centimeter, you've got to make this transition in pressure and density, and so that the atmosphere is roughly, it's not just exploding away, it's in some kind of stable equilibrium on a global scale. And so what you've got here is photons that are gradually leaking out more and more and more, and only in particular cases like the cores of things like a magnesium line, H alpha, calcium, these very, very strong lines in the spectrum can absorb things in the chromosphere. But the problem here is we're not in the coronal limit where we have maybe 1 scattering of a photon. You've still got short photon path lengths stuck inside this layer of the atmosphere, which try to keep the populations up. So it's trying to approach equilibrium, but they keep escaping. And so now we've got a situation where these two are partially coupled. The photon pool and the plasma pool of it contains energy in these regions, which are you have to solve for simultaneously, and this is called non-LTE. And this is what HAO was famous for, along with the University of Colorado. People like Dick Thomas, Grant Athay, Dmitry Mihalis, Lawrence Auer. You know, this is the contribution. One of the contributions inherited from people like Menzel and Roberts and people of the Colorado community to the understanding of the breakdown of these two simplifications, local thermodynamic equilibrium and the corona. And it's a very tricky region which has taken is still evolving today. And the ways that we solve those problems have become very elegant, incorporating what we know about analytical physics as well as very clever numerical schemes. And the whole point of that is to solve for the two distribution functions, one for the particles, one for the photons, but still assuming mostly these days that the collisions are fast enough that the particles are definitely in some kind of a Boltzmann distribution at a local temperature that's different from the electrons. The free particles are in a Maxwell-Boltzmann distribution. But now we're in a state where the internal structure of the atoms is well out of that situation. So what we have is a radiation field, which is decoupled or partly coupled, and we have electrons which collide each other a lot, and we assume those to be, because they move fast, they're very light, they have a strong charge, and we assume that those and the ions are coupled strongly so that they form a Maxwell-Boltzmann distribution. On the other hand, the internal structure of the atoms, remember we have the hydrogen atom with n equals 1, 2, 3, 4, and 5. Those internal degrees of freedom of the atoms that we have are the things that emit the line radiation that we're going to be using, and those are quite a long way out of thermal equilibrium. So you would make a huge error in writing down the distribution of particle densities using the local electron temperature there. They're determined by the interaction between the particles and the radiation. So let's recall some things here. Going back to, first, second year undergraduate physics, we have the Maxwell-Boltzmann distribution. Again, this is just the case where the assumptions behind this are, made clear to us as students. We have, the Boltzmann showed that any system allowed to relax on a long enough time is going to try and approach this thing because of the stochastic kind of collisions between particles. And that describes the number of particles between velocity v and v plus dv, and we have the standard equation there. Now, then when we have, and then we use the notation of v sigma. This is in orders of magnitude, in dimensions is v is velocity, sigma is a cross section, which is just the probability of something happening. So that equation, the second equation, just shows you a number which is in centimeters cubed per second for the probability of an event described by this particular cross section sigma. That could be photonization, collisional excitation, could be de-excitation, could be anything, any change of state from one quantum state to the other one. And this just describes a number which is in centimeters cubed per second, which when multiplied by the actual density of these particles, instead of writing it as a function of velocity, we integrate out the velocity and we keep it as a function of space, and we get the density of the particles. Then you just multiply this number, centimeter cubed by second, by the number per cubic centimeter, and you get the speed, the average probability at which any given atom is going to make a transition, or is going to be described by the probability sigma of occurring in the number per second. Okay. All right. Now we know that there are some relations here that must occur in thermal equilibrium, and the numbers of say we have two atomic levels, 1 and 2. that each one has a degeneracy of G, and the energy difference between them is this, then this is the equilibrium condition for the ratio of their populations. It's just a Boltzmann factor, okay? But we know we've got this extra thing called ionization going on. And so if we go down to the bottom of the equation, we now have instead of the ratio of, say, the n equals 2 level to n equals 1 level of hydrogen, which we can write down in thermal equilibrium like by 5,115, we now want to know what the population of protons is, Q of Z. So Z would be like 1. So that would be the first charged ion of hydrogen, which is just a bare proton. And the ratio of that to the number underneath, which is equivalent to 5,115, is given by this number here, by this formula here, derived by Saha in about 1920. And this is what Cecilia Payne-Koposchkin was able to use to show her remarkable results we talked about at the beginning. So now, instead of a degeneracy of levels, we have a partition function, exactly as we'd expect. The UZ is the partition function for protons. It's basically the number 2, because a proton can have one of 2 spin states. And underneath, we've got the partition function for the hydrogen atom, which is, again, computed in equilibrium. So it's the sum over all states weighted by e to the minus delta E over KT. It's the traditional function for Maxwell-Boltzmann distribution, all summed up over all bound states. In a vacuum, that's an infinite sum, so there's a problem, right? In a plasma, it's not a problem, as we'll get to. But what you can see here is, and it's very nice dimensionally to see this, is that we have the same kind of ratio for a thermal equilibrium gas. The electron density times the ratio of the protons to hydrogen atoms is given by this formula on the right. And you can see, if I move the lambda t, what's lambda t? It's actually the thermal de Broglie wavelength. So you can see that if I move that to the left, the dimensions of lambda t cubed times Ne cancel out. So we've got a volume. It's a volume. Lambda t cubed is a volume. Ne is number per volume. So we have basically a dimensionless equation there with just describing. So it looks exactly like the equation for Maxwell-Boltzmann, as you'd expect for the 2 bound states, but it involves this expression for the volume occupied by the electrons in a space available to them, in just the same probabilistic way as the arguments that Boltzmann used. So if you're interested in that and want to look at a nice derivation of this, there's several ways to do it. Feynman has one way of doing it in his first book, actually. But also Cooper has an elegant derivation based upon minimizing something called the Helmholtz free energy. Okay, so this is the thermodynamics of particles. Now, what about the thermodynamics of radiation? Well, we know that the Planck function from the work of Planck and other people, to avoid the ultraviolet catastrophe, we have the -1, we have the expression here for, and this is the distribution function for photons, which of course is in thermal equilibrium here, and those are bosons. So we have the boson Bose-Einstein kind of statistics here. So thermal radiation, it's fixed at each frequency, it's just fixed by the temperature. Density doesn't enter or anything like that. It's just a number, and it's called black body radiation. Okay. So now, what we're going to do is later on, we're going to find out in a couple of weeks' time that the radiation emerging from a body at that temperature, what you do is you go down 1 photon mean free path roughly into this thing, and you ask the question, what is the local temperature 1 mean free path of the photons in that corresponds that we find that's going to characterize the emergent radiation? And it's really an integral, but this is a 1-point expression or 1 depth expression, and this is called what's it? I can't remember the name of it now. it's when you look one optical depth into the atmosphere, you see the radiation that's emerging, okay? And what we will do is in LTE, we can write the source function like this, B nu. We know exactly what the temperature is. We know what the radiation is. And so the emergent radiation is this approximate so-called formal solution. The intensity that we see is roughly the Planck function at tau equals 1. And this is why the sun looks like it does. Tau equals 1 happens because of the absorption of H minus throughout most of the photosphere. And so what we see is we see down to that H minus depth, and it comes out to be about 5,500 to 6,000 degrees corresponding, which is what we showed earlier, okay?
Is that the Eddington-Barbier relation?
Thank you, yes, you rescued me from that. That relation there, I nu is approximately equal to B nu tau equals 1. If I were to replace the B nu by an S nu, by the actual source function, which well, I haven't defined yet, but it's the amount of emission along one mean free path, essentially. And that's, if it's decoupled, then that's a non-LTE problem. But that is the Eddington-Barbier relation right there. I nu is about the source function at tau equals 1. So that's the emergent radiation. Okay. Now, the source function in non-LTE is in one very nice approximation called complete redistribution. That's just simply saying that when you have a scattering of a photon by an atom between two levels, the radiation that's emitted has the same frequency distribution unconnected to the incoming radiation. Now that is complicated, but that's not the point I want to make here. Well, the point I want to make is you can see the direct analogy between B and S here. And in equilibrium, they're the same, as you can see, because N1 divided by G1 divided by N2 divided by G2 is nothing other than exponent H nu over KT. So here we have something in the general case. So if we were to solve for these number densities, N, this is the number densities inside the hydrogen atom or the calcium, whatever it is, then we know what the radiation is going to be, even when it departs from that particular case of equilibrium, which is given by the Planck function, okay? And that's a non-LTE source function. That's basically when we don't have sufficient density, the photons are leaking out, we maybe have steep gradients within the atmosphere and temperature and things that make it depart locally from the local temperature. Whatever it is that's going on, we now have a sort of understanding of roughly what's going on in terms of the source function. And so what it means is, imagine now we got a case where we try to use these two expressions in the middle of the chromosphere. I told you that the top one will be wrong because it's going to be wrong because that is not going to be equal to N1 over N2 with the G factors involved, right? Instead, you're going to have a case where photons are escaping so that N1, the photons are leaving. So there's nothing arriving to keep that N2 population up relative to N1. So what this means is the source function, generally speaking, is going to be lower than the Planck function when you come further out, because the detailed balance is not there anymore. And so you're going to have a much larger value of N1 divided by N2. And so that denominator is going to get very big, which means the sources are going to get dropped. That's why we see an absorption line in like calcium. You have this huge dip around 3969 and 3933 angstrom in the spectrum, which is so obvious. I mean, it's a huge notch out of the thing. And that's because the source function can't keep up with the Planck function as it's going out. And so there's very much less radiation. And the further out you go, the closer to the line center you get, because it's more opaque there, and both photon mean free paths are much smaller there, the lower the temperature gets. So it's telling us that when we see these absorption lines, the temperature is dropping. And in an LTE case, like iron 1, source function can be very close to LTE. Opacity is different. I mean, there's subtle things going on here, but in general, what you find is you see these absorption lines. So now we've got a basis for understanding how these absorption lines work. So let's just remind ourselves, the non-LTE problem is to solve the distribution function for photons that is consistent with the plasma distributions for the free and bound particles, where pretty much the free particles are in thermal equilibrium because they're free and they bash into each other very quickly. Their reciprocal processes are very strong. So you have a temperature of the plasma, say, but where the density is given by this thing here. But inside the atoms, the distribution is very much non-LTE, not in detailed balance. So let's look at the principle of detailed balance again. In a little more detail. Corresponding to every individual process, there's a reverse process, which then if we go in a state of equilibrium, the average rate of every process is equal to the average rate of its reverse. I'm just reiterating, this is what Boltzmann was working with, Maxwell. And we can do an example here. For instance, around 1916, before the development of quantum electrodynamics with Dirac in 31, and then people like Feynman developing it much later on, there was a formalism by Einstein, which was phenomenological, based upon observations and measurements. He proposed that there were two kinds of mechanisms of coupling of photons between these states. One was a spontaneous emission, and one was absorption, and one was emission. So that if you have a quantum jump between two levels, it can jump from the upper level J in that equation via spontaneous emission, and the photon just goes on its merry way. So you've pulled out of thin air, you've pulled out, or not even air, out of a vacuum, you've pulled out a photon, and it's allowed this hydrogen atom to decay from one excited state to another one. Turns out that that's a quantum electrodynamic phenomenon, which is pretty, interesting. You're pulling a photon out of a sea of a vacuum of, one way of looking at it is you have this sea of bubbling stuff going on in the vacuum. The vacuum has zero energy, but of course you've got the uncertainty principle, and you're allowed to borrow a little bit of that for a very short time, providing you're careful. So what happens is, but anyway, Einstein came at this phenomenologically, and the question then was, how on earth do we figure out what these coefficients could be? So the way that Einstein did this, and the way you can figure it out, is rather straightforward. You say that we have thermal equilibrium between these processes when you posit that in thermal equilibrium, these must obey the micro time reversibility. So this is the basic physical assumption of the detailed balance. Okay, so it's Newton's equations are symmetric in time. So a given process, you can't tell where you're going one way or the other. And the definition of equilibrium through detailed balance is identifying that those equations of motion are not dependent on the direction of time. So what we have here then is that equation, the first equation on the bottom there. We say that for any given state, we have an average number of particles in the state J. It decays via spontaneous emission A, but it also can decay by stimulated emission. So you've got a photon coming in, and this is entirely out of Einstein's head, in which you say it's going at and the more photons you have, measured by some moment of the distribution function of the photons, which is called J, at the mean intensity of the radiation, times a constant, because the more photons you have, the more likely it is to interact for a given cross-section of probability. So these two processes must add up in this form, AJI plus the intensity of radiation times J, and that's got to equal, in equilibrium, it could be an out of thermal equilibrium if you want it, but it has to equal the rate going up if you have just two levels in an atom in the universe and a radiation field. Okay. Now we say, well, let's impose equilibrium. So we know exactly what Nj over Ni is. It's Maxwell-Boltzmann's number, and we know the frequency of the jump, the energy jump between the levels, h nu, and we know the temperature. So we can just stuff those Ni and Nj into the left-hand side there. And furthermore, because we know it's equilibrium, we know what the source of what the radiation field's distribution function is given by the J. So we've got an expression for J in terms of temperature and frequency. We've got an expression for Ni over Nj as a function of temperature and frequency. So we should be able to figure out what A, B, and the A's and B's, how those are related, and we'll do that in a moment. In a very nice thing that isn't terribly well known, but I found to be really, really nice, interesting piece of work was Ionosphere in 31, who analyzed linear departures from equilibrium states. So for instance, you'd write T equals T0 plus a little t plus dt by dx, say in that direction, times dx. So there's a small correction to the local temperature, right? And so it's not just one point in space, but you allow that there to be an asymmetry in the local distribution function of the particles, the free particles. And then what he did was he looked at linear departures from these equilibrium states and derived the general formalism for transport coefficients. And he calls them thermodynamic forces. And you have these beautiful reciprocity relations between the transport. And so it's as general, I mean, it's so general. He's a chemist, this guy. He got a Nobel Prize in chemistry. But you've got this beautiful formalism for saying how physical systems transport different kinds of energy, electric charge, neutral particles, whatever it is that's being driven by some departure from equilibrium. And I just absolutely love that formalism, and it's still used today. And for instance, your coefficients of things like elasticity, thermoelectricity, all this stuff comes from this original work by Ionosphere. All right, now I'm going to scare you to death by showing you some horrible things, and we're going to take a list. Remember, Einstein postulated those three processes. After Dirac came along, it turned out that this was fully supported by quantum mechanics, and so those first three cases are things where we have described just now. In terms of those populations and the relationships of the atomic states. And here I happen to have chosen again what looks like the beryllium atom. And so we've got an excited level, for instance, spontaneous decay. We got a 2s squared ground state. There's a 1s squared underneath, a completely full shell. We got a 2s squared lowest level of this beryllium-like ion. But if we happen to knock it in some fashion with a photon or electron or electric field or something, then this state singlet P odd can decay down via Einstein's process. And we see a photon. And in fact, one of the brightest lines in the spectrum of the sun, 977 angstrom, occurs in this precisely this state for doubly ionized carbon. Okay. And then we have stimulated emission where we have two photons coming out. We have absorption, so we can take a photon, we can hit the ground state and knock it up into that state. But now we also have these other things where this notation it's always going to be clumsy because it's you have an ionization stage I, and you have a level within that ionization stage of J. So. But basically, just remember that these are the same things here. So we impact an ion, say, the 2s doublet s half lithium-like ion with electron, and it joins, it sticks onto the atom, but it occupies a new state with two electrons. Remember, the electrons can't be in exactly the same state, but we have a spin space that they can slot into, and the lowest energy state of that one is a 2s squared state. And so it comfortably sits there after, but it's emitted a photon so doing. So what's happening is the electron has moved in, it's been grabbed by the atom, and it's precisely that frequency of the incoming kinetic energy plus the ionization energy of the particle, of the beryllium-like ion. It's emitted a photon at that frequency, and that's called recombination. The reverse of that is just photoionization. And the only difference between the 1, 2, and 3 and 4, 5, and 6 is that instead of having photons moving states between bound states, you've also got photons moving things between bound and a free state. So you can think of an atom as being consisting of, say, in photoionization, you've got a change from one ion to the next, to a more ionized ion with a free electron. So that's the only difference, is that you've got this free electron going around. Okay. So now the answer to Einstein's problem turns out, if you do the algebra, it just turns out to be as follows. Remember, we've got sort of two equations, two unknowns. So we've got two relations we can get from that. And here they are. And so when you use Einstein's formalism, backed up by Dirac's formalism or what have you, in terms of physical understanding as opposed to just phenomenology, then we have a complete description at a certain level of approximation as to why atoms can interact with photons. And we have a way with the thermodynamics of those two pools of energy to figure out the relationships between those things. Okay, 15 minutes. So let's just summarize one or two things here. Processes causing plasma radiation between quantum states. And this, remember, is what we were talking about. It's not just spectroscopy of the atoms. We want to know what we can learn about the plasma from these kind of interactions. So we really must understand this stuff. First of all, we can look at the classical physics. Electrons have a very large charge to mass ratio. And so in any energetic plasma, if you just work out what kT over m is for a typical plasma, which is sufficiently ionized, you get a very high velocity for the electrons, 40 times lower for hydrogen, whatever, heavier for the heavier ions, okay? So, but if I embed those electrons, if I embed an atom inside that bath of electrons, then what do they see when they approach an atom? They see a cloud of electrons around with a nucleus. The nucleus anchors those electrons in place through the strong electrostatic interactions. And the incoming electron then is not really going to interact with the proton because it's shielded by the electrons. What's going to happen instead is, and I'm going to make a qualitative statement here about what's going on and why this is so important. The electron comes in and it sees this bunch of electrons in some stochastic way, because the quantum mechanics is bubbling and the electrons aren't steady or anything like that. In comes this electron with a certain energy, and it sees one of these electrons and it says, I'm going to exchange a whole bunch of energy with you. And that's maximal when two particles have the same mass, classical mechanics. If you just work out 2 billiard balls, of the same mass, you maximally exchange energy between the two balls as they collide. If I were to put a P and a billiard ball, then the billiard ball would just plow right on through the P and there'd be no exchange of energy very much. So that's the way to think of it. What this means is that the probability of any particle, like an ion coming in, like an electron, like a molecule, of changing things inside this plasma is maximal for the electrons. So the electrons are the things that, generally speaking, to zeroth order, clobber the atoms and make them respond. And this is the light we see as a result of the interactions with the electrons. Okay. Now, the probability of that happening, again, I've introduced this very much earlier. The probability per unit time is simply this dimensionless, or this quantity that turns out to be seconds to the -1. You impact with velocity v, you have a cross section which again measures probability, and you whack this thing, and if you have n of these electrons in the plasma at any given time hitting this thing, then you take the average over the collider's distribution function, which is a Boltzmann one. You get a probability of NA times this, and that has to be a function of temperature, because the average over the collider's distribution function over V is over R is the temperature by definition. So this thing is going to be a function of temperature, whatever it is, the probability. We also know from Einstein that there's a photoelectric effect, so that for any process to happen, if it's in a bound state in a potential well, then there's an E you have to get to before you can make that sigma non-zero. It's exactly what Einstein said with his photoelectric effect. There's no effect until you reach the energy, critical energy. And so you know that this probability is going to be proportional e to the minus delta E over KT. So that all these things, what they're going to look like is NE times e to the minus delta E over KT. And now you understand how an atom is going to interact with the electron around the atom. Now, in QM, of course, we have, let's look at the, so that's basically a classical distribution of the, that describes qualitatively how we expect an atom to respond to exchanging thermal energy with the plasma like that. In quantum mechanics, we've got, if we now look at the atom sort of on its own, without embedding it in this plasma, we've got electrons, within the plasma, we've got electrons flying around, which we know are going to have maximal impact. We can probably ignore things like protons, hydrogen atoms, not always, but it's a good first guess. And then we have a challenging computational problem here, because what we have is, no matter whether we've got a hydrogen atom, which has got one electron around it, every single atom has at least one electron around it. And if an electron is coming along, then we try to treat it in a perturbative way, like each atom operates individually, and you've got this electron coming in, then we've got a many-body problem. So we've got one electron tied to a hydrogen atom interacting with another electron. That's a three-body problem already. So now we know we're not going to have closed-form solutions. There are many ways to limit the probabilities using various arguments, and I'll do one in a moment to demonstrate precisely what I'm talking about. Now, the target, so we can imagine now we've got an atom which is a target for an electron coming in, and what we're trying to do is find out what the nature of those electrons is. Say the temperature of electrons is in the corona from the radiation coming from this target. Target has two levels, has two particles, a proton and an electron, say hydrogen, and we whack this thing, but the target and the electrons around the atoms are identical particles, right? We're not impacting it with muons or something, so because those are going to be pretty rare things with a short lifetime, something like that. So what's going on here is that, as well as just coming in and knocking the electron off, one can come in and replace the electron, and not the other one happens to go away. So this is a many-body sort of interaction, and these things turn out, when you look at the physics of it, something called dielectronic recombination, you can get doubly excited states before it knocks off. So that means all that is saying you got an electron coming in, hits a hydrogen atom, it temporarily gets glued to the hydrogen atom, it becomes an H minus, right? That can happen. And the H minus, because it's got a spin up and a spin down, and then this thing can then relax and go down to a lower energy state and send off an electron. That's one possible scenario which could happen during these collisions. Now, the exchange term, you'll read in the literature things like direct ionization and exchange and auto-ionization. These are all just various possibilities which we must take into account for a many-body system to evolve in time, so that we can evaluate all these sigmas that we have there. That's all they are, okay? One of the things that's very important is that the electron distribution function, if it's going as e to the minus delta E over KT above threshold, then the threshold is obviously really important. I mean, if you require a certain amount of energy to make something happen, it's the electrons very close to that energy which are going to be most important if the electron's in equilibrium, because they're falling off as e to the minus the energy of the electron divided by KT. So what we have is, we know that the near threshold, when we get near threshold, so just above the energy needed to make Einstein photoelectric effect work, that's where we need to know the cross sections extremely well. And so all the technicality of this stuff, and you can see, I've got two electron excitations, complex resonance structure, auto-ionization, ionization, dielectronic combination, the names are all there. This is all that's going on, is that you've recognized that we better get close to threshold. And when you're close to threshold, there's only just enough energy to affect things. It's not like you're coming in with a nuclear bomb and knocking the electron clean out without, and it's just got so much energy, the incoming electron, that there's no question about the threshold being important. That's the kind of thing you can use with a Born approximation, which is a way to simplify these kind of calculations. And that could work very well. No, we know that the Born approximation is not going to be good in most plasmas. We're going to have to deal with complicated structure. I'm going to finish here with a demonstration to give you some confidence that it's possible to calculate these things from first principles, right? So let's do something that was done very cleverly by Thomson in 1912. I think that was Lord Kelvin, wasn't it? That Thomson, I can't remember. Anyway, consider the following problem. Let's pretend we've got an electron sitting around a hydrogen atom, and take my picture I described just now very literally. We've got a proton and an electron, and we're not going to do quantum mechanics here. What we're going to do is we're going to say, well, the incoming electron is going to share its energy with the electron that's there. It's not going to share its energy with the proton because it's got way too much mass to share much energy. The electron's just going to bounce clean off it elastically, pretty much. So what we can do is we can say, well, we know it's at the bottom of a potential well of depth W. So that's the number of electron volts I need to knock off a hydrogen atom. And so what we'll do is we'll compute for a given impact parameter, namely the electron's coming in at very large distance, and it's got a perpendicular distance of r in the impact parameter. And we say, what is the amount of energy that I can give to this electron, assuming that the proton is not relevant at all? So that's a big assumption. I mean, that's silly. But we're pretending this electron is just buried at the bottom of a potential well. And we say, what is the amount of energy that I'm going to exchange? Well, it turns out if you do the sums, you get this quantity here, which says that the amount of energy shared by the incoming electron with the other one is simply this. Okay, so it goes as sort of roughly the energy squared, foot to the power of 4, with some corrections there. Now what you do is what we say, well, the cross section is defined as the probability for each impact parameter r times the area. So we've got 2 pi r dr there. So that is the rate at which we expect to knock the electrons off the hydrogen atom classically. Okay. And following Thomson, then we can assume that, well, what can we do? For every impact parameter, if we've got enough energy for that parameter, then we make the probability 1, or 0 if we don't have that amount of energy. I mean, it's incredibly naive, right? But let's just follow it along. Okay, so now when you do that, you end up with an expression that looks like a combination of 130 and 131. And so you end up with an expression for the cross section at the bottom. So the classically, you've added now some stuff from semi-empirically from the knowledge of quantum mechanics of hydrogen, namely the ionization energy, and you end up with an expression that looks like this. Okay, so that says for an incoming electron with energy half mvi squared, W, that is the cross section as a function of that energy. Now, we simply put in a Boltzmann distribution, integrate that thing up, and we end up with an expression that looks like the middle expression here. So as I said, we get something that looks like e to the minus I over kt. So now you can see, I mean, and if we put the numbers in for the sun's atmosphere, say, at the top of the chromosphere where the hydrogen lines are formed, I is 13 electron volts, but kt is about 1 electron volt or a bit less. So that's a very, very large exponent, negative exponent. Okay? So there is then this thing called the semi-empirical formula, which is actually a quantum mechanical sort of semi-empirical fit of quantum mechanical calculations and measurements to this formula. And let me show you what it looks like. Notice the linear Y scale. That's the cross section. It's not 10 to the 2 or 10 to the 1. It's 1 or 2. And what's shown here are some classical theory of neutral atom ionization. And using the expression we just shown. And there are the experimental cross-section is given by A, I think. I mean, it has no business being anything like this good, and yet there it is. So you have some kind of qualitatively understanding. And the real issue with the quantum mechanics is to calculate the, instead of calculating the probability P of R as a function of some classical radius, you have to calculate it in terms of its quantal equivalence, and those are given here. So this is all part of the same argument here. But now, so at the end of all this today, what we've done is I've tried to introduce you to various kinds of approximations that we talk about in radiative transfer, in the physics of spectroscopy of astronomical objects. But I've also shown you, I think, some of the needed necessary things to compute the rates at which energy is exchanged and photons are emitted and all this other stuff. And the example I've given you of impact ionization, that carries through quantum mechanically into all those things like the Einstein A coefficient, recombination. All these things are computational on the same principles as we just took, as I just showed you there. So in principle, what you have is a sort of, Richard Feynman kind of understanding of the bits and bobs that add up together. And we haven't got to the point where I've shown you a simulated spectrum yet, but that's the ultimate goal of this thing, including the effects of radiative transfer, which I haven't finished the lecture on that yet, but that'll be later. But what you've got here is the ability to say, for a given temperature and a given density of plasma, I think these processes are going to be important. I know that we have to get very good probabilities at threshold. I know that the SAR equilibrium will work under this density approximation. It won't work in the corona. We need to consider all the detailed balance there or not there, based upon Newton's laws of time irreversibility. And it's all there. It's just very straightforward physics, but it gets translated into some bloody awful looking things when you look at the actual calculations people. I mean, cross sections have resonances, they have, differential cross sections for different states of polarization of the electrons and the photons. I mean, it's a mess, right? But it's all just detail. It's important detail if you really want to understand how the plasmas are evolving. But I hope you can see how the plasma is affecting these atoms and how they might be able to tell you about things like temperature and density. So later on, I'll show you, illustrate to you what some of these processes look like, show you how to calculate various kind of things, the many body problems of 2 electron atoms. Again, this looks horrific. I mean, who wants to look at that? It looks like nuclear physics to me. I mean, I hated that when I was a student. And so, but there are ways to understand this. And at the end of the day, what we're going to want to do is this, which we started with. So right now, we've defined something about the plasma. We've talked about atomic data. We've got some of the statistics done. We've got the collisions. We've got the radiative cross sections, and we will be in a position to calculate the spectrum intensity the next time. All right, so my mouth is very dry now, oddly enough. I can't imagine why. But thanks again for your attention. If anybody has any suggestions, any questions or anything, I'd like to hear them, and otherwise we'll see you next week, hopefully.
Let me ask a very naive question.
Yep.
So you were saying how you wouldn't expect that when you were looking at the Thomson cross section on those, what I'm going to call basic assumptions.
Yes.
And yet it turns out to be pretty damn good.
Yeah.
Is this because we are looking at it from a quantum mechanical system, maybe something rather basic in the sense you're looking at an electron and a hydrogen atom? Is that one of the reasons it's doing so well?
I don't know.
If we had a more complicated system. Because you have the probability.
Yes.
There's the quantum mechanical part.
Right.
But what is that? What
I think what's going on is that, remember we talked about, so Joan's question is about the Why is it
so good?
unreasonable? Why am I
Yeah.
surprised that it works so
And the
well?
distances are large, gigantic compared to,
Yeah.
well, Planck scales,
Well,
but.
So
why is it-
first we ignore anything about the existence of a proton there, except that we know that the electron is in a potential well to start with by virtue of that. So when you look at the more detailed atoms that have various internal degrees of freedom, if I now shoot the electron at the hydrogen atom at just over the threshold energy, it can knock this off, and you'll get the cross section that Thomson calculated. Now, if the electron comes in but doesn't knock that one off, but temporarily forms the H minus ion. Now, H minus only has one bound state. That was proven some time ago. Whereas most complex atoms, if I would say like helium, if I hit an electron with it, I end up with a situation where in that potential, just above the threshold, not only can I excite both electrons end up forming a state like H minus, right? Except that they're now orbiting, and there are many of these states. So what that means is that the uniqueness of only one bound state of H minus there means that the effects of, including the effects of many-body and the capturing of electrons by the H atom to form an H minus ion, there's only one state that can contribute to that. Whereas the other ones have many, many, many more. And these things, so you end up with an electron, say, in the n equals 2 level of helium, and then this other incoming electron, it's shared most of its energy with the n equals 2 electron, but it's found itself in a state which is in, say, n equals 20 itself. It's not free, it's still bound. And now I can do the n equals 3 electron, and so those 2 electrons are still bound, both in bound states. Now they're unstable, so one of them will decay, and then it'll end up with this electron either being captured or knocked off into space. So then it's the number of internal degrees of freedom of the n plus 1 atom. So you got helium has 2 electrons, and an incoming electron is going to make 3 electrons, and those 3 electrons can find themselves with 1 electron right down in the well, but with both 2 outside electrons excited. And it's those kind of things that really screw up any kind of classical. There's no classical equivalent. But in hydrogen, I think you might be right. I think.
Yeah, because you have a very complicated wave function in that example you just gave.
Yeah.
Right? I mean, that's very difficult.
And one example here is something that looks like this. The amazing thing is we have you can't tell, but that's a mix of theory and measurement of these resonances of the internal structure of iron, happens to be iron 18. So all those resonances are these doubly excited states. Hydrogen only has one of those, right? So that's why I think perhaps one of the reasons. I mean, you're right. That's a good question. I hadn't thought of that. Maybe my argument is actually wrong, but that's my initial thought.
Yeah.
But here, I mean, what's astonishing here is to the level of 1 part in 10 to the 4 or something, when you've got such a very highly ionized atom, the central pull is so strong that these states are very, very well defined by they're not flaky, they're strongly bound, and so they're relatively easy to calculate the energies of these things. And there they all are. They're all in the right place with the right magnitude. It's really astonishing. And these things are essentially cross sections, rate coefficients. Again, centimeters cubed per second. You multiply that by the electron density, and you get the rate at which a hydrogen, an iron atom will recombine. I think this is an amazing plot. This absolutely shocked the hell out of me when I saw how well they were doing. And it speaks to Tom's question in the first week as to, surely you can compute things very well. And the reason this works so well is because it's a very highly ionized atom in which the 0th order Hamiltonian is extremely well defined by the central field. Senor Thomas.
Yeah, you made, I think, a really good point about the importance of thresholding, that there is a photoelectric effect and you have to be above a certain energy. So that's really usually very far out of the core of the electron distribution function. So
Yep.
I want to come back and ask, how can we be certain that the tails are Maxwellian?
Well, we can't. It's a matter of faith at this point in most plasmas. I guess you can, because after all, let's think about it. We're looking at the photons that emerge, and those photons are all caused by integrations from threshold to infinite energies. So you can have a Maxwellian that has the same integral as a non-Maxwellian, and it's quite hard to tell the difference because of the integration over all energies of the particles.
That would be true, but the temperature would be different for the Maxwellian.
Yeah, and in fact, how are you going to define the temperature? As some kind of width of the distribution in some sense, in which case, or if you could imagine doing a bisector and saying, well, temperature in the core is 10 to the 4 Kelvin, and temperature in the wings is 10 to the 9 or something. I mean,
Right.
So, but that temperature doesn't mean anything really, not in a thermodynamic sense, perhaps. Yeah, but I mean, you've hit the nail on the head here. We don't know, and I don't know how to tell that, except when electrons get high enough energy and there's sufficient number of them that you start to see things like synchrotron or gyro-resonant emission in magnetic fields, for instance, because those things scale with the power of and they can become polarized. Furthermore, they can become, relativistically, those kind of processes become very, very anisotropic. So you could look at anisotropy in radiation, and we know there are non-thermal particles in active galactic nuclei and stuff because of the anisotropies and the polarization of the radiation we see there. What we're more familiar with as the sun is that most of the time we don't see things that are obviously like that, but during flares we do.
Yeah.
Right? I mean, so I would keep an open mind as to what the distribution function looks like, and try and find ways to convince people that it's not. And there are people out there that do this, like chap from Cambridge, Yaroslav Dudik. I mean, it's a funny name, but he's sure that there are these kappa distributions, and uses them to analyze solar data. That's every bit as reasonable an assumption as a Maxwellian is. It might be more reasonable, but the problem is you've got extra free parameters now, and I don't know how you invert the plasma radiation to get at those free parameters in a unique way.
If you could take observations in several different spectral lines simultaneously, which had a sequence of gradually increasing thresholds,
Yes.
wouldn't that, because you're looking at different integrals that overlapped, wouldn't that give you some indication of the nature of your tail? Have people done that?
That hasn't been a very popular thing to do. I'm sure people have done it, not in recent years like that, but Dudik is a guy that you might look up, Dudik, in this regard. He gave a colloquium here, or an NSO something, in the last couple of months, which may be recorded, which might be fun for you to look at.
Okay, thanks.
Yep. Well, I got to get back and take my dog for a walk, but thanks everyone, unless you have a question. Really appreciate being able to share what I know again, so thanks a lot for listening.
Thank you, Phil.
Yeah.
Thank you so much.
Thanks, Phil.
Yeah.
I think we need to talk